हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। और आज हम करने वाले हैं क्लास 11th यूनिट 12 सम बेसिक कॉन्सेप्ट ऑफ केमिस्ट्री का पार्ट 2। इसका पार्ट 1 मैंने पहले ही अपलोड कर दिया था। आप लोग डिस्क्रिप्शन में जाकर के, जिनको नहीं पता है वो वहां से लिंक अवेलेबल है, देख सकते हैं। और बच्चों, ये स्पेसिफिकली सिर्फ और सिर्फ एक ऑडियो बुक है, ना कि एक्सप्लेनेटरी वन। सो व्हेनेवर यू आर लिसनिंग इट, बी स्पेसिफिक विद दैट। और अगर आपको लगता है कि ये वीडियोस, आपकी ये ऑडियो बुक्स हेल्प करती हैं आपके रिवीजन में, तो प्लीज इसको लाइक जरूर करिएगा एंड अपने दोस्तों के साथ ज्यादा से ज्यादा शेयर करिएगा। सो चलिए स्टार्ट करते हैं 12.7.5 इंडक्टिव इफेक्ट। When a covalent bond is formed between atoms of different electronegativity, the electron density is more towards the more electronegative atom of the bond. Such a shift of electron density results in a polar covalent bond. Bond polarity leads to various electronic effects in organic compounds. Let us consider chloroethane, in which the CCl bond is a polar covalent bond. It is polarized in such a way that the carbon 1 gains some positive charge and the chlorine some negative charge. The fractional electronic charge on the two atoms in a polar covalent bond are denoted by symbol delta, and the shift of electron density is shown by an arrow that points from delta positive to delta negative end of the polar bond. You can see here. In turn, carbon 1, which has developed partial positive charge, draws some electron density towards it from the adjacent carbon-carbon bond. Consequently, some positive charge develops on carbon 2 also, whereas delta positive symbolizes relatively smaller positive charge as compared to that one on carbon 1. In other words, the polar CCl bond induces polarity in the adjacent bonds. Such polarization of sigma bond caused by the polarization of adjacent sigma bond is referred to as the inductive effect. This effect is passed on to the subsequent bonds also, but the effect decreases rapidly as the number of intervening bonds increases and becomes vanishingly small after 3 bonds. The inductive effect is related to the ability of substituents to either withdraw or donate electron density to the attached carbon atom. Based on this ability, the substituents can be classified as electron withdrawing or electron donating groups relative to hydrogen. Halogens and many other groups such as nitro, cyano, carboxy, ester, aryloxy, etc. are electron withdrawing groups. On the other hand, the alkyl groups like methyl and ethyl are usually considered as electron donating groups. 12.7.6 Resonance structure. There are many organic molecules whose behavior cannot be explained by a single Lewis structure. An example is that of benzene. Its cyclic structure containing alternating CC single and C double bond shows inadequate for explaining in benzene's characteristic properties. As per the above representation, benzene should exhibit two different bond lengths due to CC single and CC double bonds. However, as determined experimentally, benzene has uniform CC bond distance of 139 picometer, that of single bond, a value intermediate between the CC single and CC double bond, that is 134 picometer bonds. Thus, the structure of benzene cannot be represented adequately by the above structure. Further, benzene can be represented equally well by the energetically identical structures first and second. Therefore, according to the resonance theory, the actual structure of benzene cannot be adequately represented by any of these structures. Rather, it is a hybrid of the two structures called resonance structures. The resonant structures, canonical structures, or contributing structures are hypothetical and individually do not represent any real molecule. They contribute to the actual structure in proportion to their stability. Another example of resonance is provided by nitromethane, which can be represented by two Lewis structure, first and second. There are two types of nitrogen-oxygen bonds in these structure. You can see here, first, second. However, it is known that the two NO bonds of nitromethane are of the same length intermediate between a NO single bond and NO double bond. The actual structure of nitromethane is therefore a resonance hybrid of the two canonical forms, first and second. The energy of actual structure of molecule, the resonance hybrid, is lower than that of any of the canonical structure. The difference in energy between the actual structure and the lowest energy resonance structure is called the resonance stabilization energy, or simply the resonance energy. The more the number of important contributing structures, the more is the resonance energy. Resonance is particularly important when the contributing structures are equivalent in energy. The following rules are applied while writing resonance structure. The resonance structures have first the same positions of nuclei and second the same of unpaired electrons. Among the resonance structure, the one which has more number of covalent bonds, all the atoms with octet of electrons, except hydrogen which has a duplet. Less separation of opposite charges, a negative charge if any on more electronegative atom, a positive charge if any on more electropositive atom, and more dispersal of charge is more stable than others. 12.7.7 Resonance effect. The resonance effect is defined as the polarity produced in the molecule by the interaction of two pi bonds or between a pi bond and lone pair of electrons present on an adjacent atom. The effect is transmitted through the chain. There are two types of resonance or mesomeric effect designed as R or M effect. Number 1, positive resonance effect plus R effect. In this effect, the transfer of electron is away from an atom or substituent group attached to the conjugated system. This electron displacement makes certain positions in the molecule of high electron density. This effect in aniline as shown as, here you can see. Second, negative resonance effect minus R effect. This effect is observed when the transfer of electron is towards the atom or substituent group attached to the conjugated system. For example, in nitrobenzene, this electron displacement can be depicted as, you can see here, the atom or substituent groups which represented plus R or minus R electron displacement effects are as follows. Plus R effect, halogen, OH, OR, OCOR, NH2, NHR, NR2, NHCOR. And minus R effect, COOH, CHO, C double bond O, CN, and NO2. The presence of alternate single and double bonds in an open chain or cyclic system is termed as conjugated system. These systems often show abnormal behavior. The examples are 1,3-butadiene, aniline and nitrobenzene, etc. In such system, the pi electrons are delocalized and the system develops polarity. 12.7.8 Electromeric effect. It is a temporary effect. The organic compounds having a multiple bond, a double or triple bond, show this effect in the presence of an attacking reagent only. It is defined as a complete transfer of a shared pair of a pi electron to one of the atoms joined by a multiple bond on the demand of an attacking reagent. The effect is annulled as soon as the attacking reagent is removed from the domain of the reaction. It is represented by E and the shifting of the electrons is shown by a curved arrow. There are two distinct types of electromeric effect. One, positive electromeric effect or plus E effect. In this effect, the pi electron of the multiple bond are transferred to the atom to which the reagent gets attached. For example, you can see here. Second, negative electromeric effect or minus E effect. In this effect, the pi electron of the multiple bond are transferred to that atom to which the attacking reagent does not get attached. For example, you can see here. When inductive and electromeric effects operate in opposite direction, the electromeric effect predominates. 12.7.9 Hyperconjugation. Hyperconjugation is general stabilizing interaction. It involves delocalization of sigma electrons of CH bond of an alkyl group directly attached to an atom of unsaturated system or to an atom with an unshared p orbital. The sigma electrons of CH bond of the alkyl group enter into partial conjugation with the attached unsaturated system or with the unshared p orbital. Hyperconjugation is a permanent effect. To understand hyperconjugation effect, let us take an example of CH3CH2 positive, that is ethyl cation, in which the positively charged carbon atom has an empty p orbital. One of the CH bond of the methyl group can align in the plane of this empty p orbital, and the electrons constituting the CH bond in plane with this p orbital can then be delocalized into the empty p orbital as depicted in figure 12.4a. See this figure. This type of overlap stabilizes the carbocation because electron density from the adjacent sigma bond helps in dispersing the positive charge. In general, greater the number of alkyl groups attached to a positively charged carbon atom, the greater is the hyperconjugation interaction and the stabilization of the cation. Thus, we have the following relative stability of the carbocations. Hyperconjugation is also possible in alkenes and alkyl arenes. Delocalization of electrons by hyperconjugation in the case of alkene can be depicted as in figure 12.4b. Here you can see this. There are various ways of looking at the hyperconjugative effect. One of the way is to regard CH bond as possessing partial ionic character due to resonance. The hyperconjugation may also be regarded as no bond resonance. 12.7.10 Types of organic reactions and mechanism. Organic reactions can be classified into the following categories. Number 1, substitution reaction. Number 2, addition reactions. Number 3, elimination reactions. And number 4, rearrangement reactions. You will be studying these reactions in Unit 13 and later in class 12. 12.8 Methods of purification of organic compounds. Once an organic compound is extracted from a natural source or synthesized in the laboratory, it is essential to purify it. Various methods used for the purification of organic compounds are based on the nature of the compound and the impurity present in it. The common techniques used for purification are as follows: sublimation, crystallization, distillation, differential extraction, and chromatography. Finally, the purity of a compound is ascertained by determining its melting or boiling point. Most of the pure compounds have sharp melting points and boiling points. New methods of checking the purity of an organic compound are based on different types of chromatographic and spectroscopic techniques. 12.8.1 Sublimation. You have learned earlier that on heating, some solid substances change from solid to vapor state without passing through liquid state. The purification technique based on the above principle is known as sublimation and is used to separate sublimable compounds from non-sublimable impurities. 12.8.2 Crystallization. This is one of the most commonly used techniques for the purification of solid organic compounds. It is based on the difference in the solubilities of the compound and the impurities in a soluble solvent. The impure compound is dissolved in a solvent in which it is sparingly soluble at room temperature but appreciably soluble at higher temperature. The solution is concentrated to get a nearly saturated solution. On cooling, the solution pure compound crystallizes out and is removed by filtration. The filtrate mother liquor contains impurities and small quantity of the compound. If the compound is highly soluble in one solvent and very little soluble in another solvent, crystallization can be satisfactorily carried out in a mixture of these solvents. Impurities which impart color to the solution are removed by absorbing over activated charcoal. Repeated crystallization becomes necessary for the purification of compounds containing impurities of comparable solubilities. 12.8.3 Distillation. This important method is used to separate 1. Volatile liquids from non-volatile impurities, and 2. The liquids having sufficient difference in their boiling points. Liquids having different boiling points vaporize at different temperature. The vapors are cooled and the liquids are so formed are collected separately. Chloroform base pair, boiling point 334 Kelvin and aniline boiling point 457 Kelvin are easily separated by the technique of distillation. The liquid mixture is taken in a round bottom flask and heated carefully. On boiling, the vapors of lower boiling component are formed first. The vapors are condensed by using a condenser and the liquid is collected in a receiver. The vapors of higher boiling component from later and the liquid can be collected separately. 12.5 Simple distillation method. The vapors of a substance formed are condensed and the liquid is collected in conical flask. Fractional distillation. If the difference in boiling points of two liquids is not much, simple distillation cannot be used to separate them. The vapors of such liquids are formed within the same temperature range and are condensed simultaneously. The technique of fractional distillation is used in such cases. In this technique, vapors of liquid mixture are passed through a fractionating column before condensation. The fractionating column is fitted over the mouth of the round bottom flask. Vapors of the liquid with higher boiling point condense before the vapors of the liquid with lower boiling point. The vapors rising up in the fractionating column become richer in more volatile component. By the time vapors reach to the top of the fractionating column, these are rich in the more volatile component. Fractionating columns are available in various sizes and designs as shown in figure 12.7. A fractionating column provides many surfaces for heat exchange between the ascending vapors and the descending condensed liquid. Some of the condensing liquid in the fractionating column obtains heat from the ascending vapors and re-vaporizes. The vapors thus become richer in low boiling component. The vapor of low boiling component ascend to the top of the column. On reaching the top, the vapors become pure in low boiling component and the pass through the condenser and the pure liquid is collected in receiver. After a series of successive distillations, the remaining liquid in the distillation flask gets enriched in high boiling component. Each successive condensation and vaporization unit in the fractionating column is called theoretical plate. Commercially, columns with hundreds of plates are available. One of the technological application of fractional distillation is to separate different fraction of crude oil in petroleum industry. Distillation under reduced pressure. This method is used to purify liquids having very high boiling points and those which decompose at or below their boiling points. Such liquids are made to boil at a temperature lower than their normal boiling points by reducing the pressure on their surface. A liquid boils at a temperature at which its vapor pressure is equal to the external pressure. The pressure is reduced with the help of a water pump or vacuum pump. Glycerol can be separated from spent lye in a soap industry by using this technique. Steam distillation. This technique is applied to separate substances which are steam volatile and are immiscible with water. In steam distillation, steam from a steam generator is passed through a heated flask containing the liquid to be distilled. The mixture of steam and the volatile organic compound is condensed and collected. The compound is later separated from water using a separating funnel. In a steam distillation, the liquid boils when the sum of vapor pressures due to the organic liquid P1 and that due to water P2 becomes equal to the atmospheric pressure, that is P is equals to P1 plus P2. Since P1 is lower than P, the organic liquid vaporizes at lower temperature than its boiling point. Thus, if one of the substances in the mixture is water and the other a water insoluble substance, then the mixture will boil close to but below 373 Kelvin. A mixture of water and the substance is obtained which can be separated by using a separating funnel. Aniline is separated by this technique from aniline water mixture. Here you can see the diagram 12.8 distillation under reduced pressure. A liquid boils at a temperature below its vapor pressure by reducing the pressure. Now differential extraction. When an organic compound is present in an aqueous medium, it is separated by shaking it with an organic solvent in which it is more soluble than in water. The organic solvent and the aqueous solution should be immiscible with each other so that they form two distinct layers which can be separated by separatory funnel. The organic solvent is later removed by distillation or by evaporation to get back the compound. Differential extraction is carried out in a separatory funnel as shown in figure 12.10, page 360. If the organic compound is less soluble in the organic solvent, a very large quantity of solvent would be required to extract even a very small quantity of the compound. The technique of continuous extraction is employed in such cases. In this technique, some solvent is repeatedly used for extraction of the compound. 12.8.5 Chromatography. Chromatography is an important technique extensively used to separate mixtures into their components, purify compounds, and also to test the purity of compounds. The name chromatography is based on the Greek word chroma for color, since the method was first used for the separation of colored substances found in plants. In this technique, the mixture of substances is applied onto a stationary phase, which may be a solid or a liquid. A pure solvent, a mixture of a solvents or a gas, is allowed to move slowly over the stationary phase. The components of the mixture get gradually separated from one another. The moving phase is called the mobile phase. Based on the principle involved, chromatography is classified into different categories. Two of these are A. Adsorption chromatography, B. Partition chromatography. A. Adsorption chromatography. Adsorption chromatography is based on the fact that different compounds are absorbed on an adsorbent to different degrees. Commonly used adsorbent are silica gel and alumina. When a mobile phase is allowed to move over a stationary phase, the components of the mixture move by varying distances over the stationary phase. Following are two main types of chromatographic techniques based on the principle of differential adsorption. A. column chromatography, and B is the thin layer chromatography. Column chromatography involves separation of a mixture over a column of adsorbent, that is a stationary phase, packed in a glass tube. The column is fitted with a stopcock at its lower end. The mixture adsorbed on adsorbent is placed on the top of the adsorbent column packed in a glass tube. An appropriate eluent, which is the liquid or a mixture of a liquids, is allowed to flow down the column slowly. Depending upon the degree to which the compounds are adsorbed, complete separation takes place. The most readily adsorbed substances are retained near the top, others come down to various distances in the column. Thin layer chromatography. It is another type of adsorption chromatography which involves separation of substances of a mixture over a thin layer of an adsorbent coated on glass plate. A thin layer of an adsorbent, silica gel or alumina, is spread over a glass plate of suitable size. The plate is known as thin layer chromatography plate or chroma plate. The solution of the mixture to be separated is applied as a small spot about 2 cm above one end of the TLC plate. The glass plate is then placed in a closed jar containing the eluent. As the eluent rises up the plate, the components of the mixture move up along with the eluent to different distances depending on their degree of adsorption, and separation takes place. The relative absorption of each component of the mixture is expressed in terms of its retardation factor, that is RF value. RF is equals to distance moved by the substance from baseline, that is X, upon distance moved by the solvent from baseline, that is Y. See here figure 12.12, thin layer chromatography, chromatogram being developed, and here you can see developed chromatogram. The spots of a colored compounds are visible on TLC plate during to their original color. The spots of a colorless compound which are invisible to the eye but fluorescent in ultraviolet light can be detected by putting the plate under ultraviolet light. Another detection technique is to place the plate in a covered jar containing a few crystals of iodine. The spots of compounds which adsorb iodine will show up as brown spots. Sometimes inappropriate reagent may also be sprayed on the plate. For example, amino acids may be detected by spraying the plate with ninhydrin solution. Partition chromatography. Partition chromatography is based on continuous differential partitioning of components of a mixture between stationary and mobile phases. Paper chromatography is type of partition chromatography. In paper chromatography, a special quality paper known as chromatography paper is used. Chromatography paper contains water trapped in it, which acts as the stationary phase. A strip of chromatography paper spotted at the base with the solution of the mixture is suspended in a suitable solvent or mixture of solvents. This solvent acts as the mobile phase. The solvent rises up the paper by capillary action and flows over the spot. The paper selectively retains different components according to their differing partition into the two phases. The paper strip so developed is known as a chromatogram. The spots of the separated colored compounds are visible at different heights from the position of initial spot on the chromatogram. The spots of the separated colorless compounds may be observed either under ultraviolet light or by the use of an appropriate spray reagent as discussed under thin layer chromatography. 12.9 Qualitative analysis of organic compounds. The elements present in organic compounds are carbon and hydrogen. In addition to these, they may also contain oxygen, nitrogen, sulfur, halogens, and phosphorus. 12.9.1 Detection of carbon and hydrogen. Carbon and hydrogen are detected by heating the compound with copper oxide. Carbon present in the compound is oxidized to carbon dioxide tested with lime water, which develops turbidity, and hydrogen to water tested with anhydrous copper sulfate, which turns blue. Here you can see the reaction. C plus 2CuO on heating gives out 2Cu plus CO2. 2H plus CuO gives out on heating Cu plus H2O. CO2 plus COH whole twice gives out CaCO3 plus H2O. And 5H2O plus CuSO4 gives out CuSO4 into 5H2O. Initially CuSO4 was white, then after it turns into blue. 12.9.2 Detection of other elements. Nitrogen, sulfur, halogens, and phosphorus present an organic compound are detected by Lasigeness test. The elements present in the compound are converted from covalent form into the ionic form by fusing the compound with sodium metal. Following reactions take place. You can see all these three reactions. Cyanide, sulfide, and halide of sodium so formed on sodium fusion are extracted from the fused mass by boiling it with distilled water. This extract is known as sodium fusion extract. A. Test for nitrogen. The sodium fusion extract is boiled with the iron sulfate and then acidified with concentrated sulfuric acid. The formation of Prussian blue color confirms the presence of nitrogen. Sodium cyanide first reacts with iron sulfate and forms sodium hexacyanidoferrate. Second, on heating with concentrated sulfuric acid, some iron ions are oxidized to iron third ions, which reacts with sodium hexacyanidoferrate second to produce iron third. Hexacyanidoferrate second ferrocyanide, which is Prussian blue in color. 6Cn negative plus Fe2 positive gives out FeCN whole 6 4 negative whole 4 negative. And in the next reaction, that is the 3 FeCN whole 6 the whole 4 negative plus 4 Fe3 positive in the presence of XH2O gives out Fe4 FeCN whole 6 the whole thrice into XH2O, that is a Prussian blue. B. Test for sulfur. The sodium fusion extract is acidified with the acetic acid and lead acetate is added to it. A black precipitate of lead sulfide indicates the presence of sulfur. S2 negative plus Pb2 positive gives out Pbs black. B. On treating sodium fusion extract with sodium nitroprusside, appearance of a violet color further indicates the presence of sulfur. S2 negative plus FeCN whole 5 NO whole 2 negative gives out FeCN5 NS the whole 4, that is of violet color. In case nitrogen and sulfur both are present in an organic compound, sodium thiocyanate is formed. It gives blood red color and no Prussian blue since there are no free cyanide ions. You can see the both reactions. If sodium fusion is carried out with excess of sodium, the thiocyanate decomposes to yield cyanide and sulfide. These ions give their usual test. NaSCN plus 2Na gives out NaCN plus Na2S. C. Test for halogens. The sodium fusion extract is acidified with nitric acid and then treated with silver nitrate. A white precipitate soluble in ammonium hydroxide shows the presence of chlorine. A yellowish precipitate sparingly soluble in ammonium hydroxide shows the presence of bromine, and a yellow precipitate insoluble in ammonium hydroxide shows the presence of iodine. X negative plus Ag positive gives out AgX. If nitrogen or sulfur is also present in the compound, the sodium fusion extract is first boiled with concentrated nitric acid to decompose cyanide or sulfide of sodium formed during Lasignase test. These ions would otherwise interfere with silver nitrate test for halogens. D. Test for phosphorus. The compound is heated with an oxidizing agent, sodium peroxide. The phosphorus present in the compound is oxidized to phosphate. The solution is boiled with nitric acid and then treated with ammonium molybdate. A yellow coloration or precipitate indicates the presence of phosphorus. Na3PO4 plus 3HNO3 gives out H3PO4 plus 3NaNO3. H3PO4 plus 12NH4 whole twice MO4 plus 21HNO3 gives out NH4 whole thrice PO4 into 12MOO3, that is ammonium phosphomolybdate plus 21NH4NO3 plus 12H2O. 12.10 Quantitative analysis. Quantitative analysis of compound is very important in organic chemistry. It helps chemists in the determination of mass percent of elements present in a compound. You have learnt in Unit 1 that mass percent of elements is required for the determination of empirical and molecular formula. The percentage composition of elements present in an organic compound is determined by the following methods. 12.10.1 Carbon and hydrogen. Both carbon and hydrogen are estimated in one experiment. A known mass of an organic compound is burnt in the presence of excess of oxygen and copper oxide. Carbon and hydrogen in the compound are oxidized to carbon dioxide and water respectively. CXHY plus X plus Y by 4 O2 gives out XCO2 plus Y by 2 H2O. The mass of water produced is determined by passing the mixture through a weighed U-tube containing anhydrous calcium chloride. Carbon dioxide is absorbed in another U-tube containing concentrated solution of potassium hydroxide. These tubes are connected in a series figure 12.14. See this figure first. Estimation of carbon and hydrogen. Water and carbon dioxide formed on oxidation of substance or absorbed in anhydrous calcium chloride and potassium hydroxide solutions respectively contained in U tubes. These tubes are connected in series, figure 12.4 as we have seen. The increase in masses of calcium chloride and potassium hydroxide gives the amount of water and carbon dioxide from which the percentages of carbon and hydrogen are calculated. Let the mass of organic compound mg and the mass of water and carbon dioxide produced by m1 and m2g respectively. Percentage of carbon, you can see here 12 into m2 into 100 upon 44 by m, and percentage of hydrogen is 2 into m1 into 100 upon 18 into m. Above also it was 44 into m. 12.10.2, that is nitrogen. There are two methods for estimation of nitrogen. Number one, Dumas method and Jaldal's method. Second one is Dumas method. The nitrogen containing organic compound when heated with copper oxide in an atmosphere of carbon dioxide yields free nitrogen in addition to carbon dioxide. CxHyNz plus 2x plus y upon 2 CuO gives out xCO2 plus y by 2 H2O plus z by 2 N2 plus 2x plus y by 2 Cu. Traces of nitrogen oxides formed, if any, are reduced to nitrogen by passing the gaseous mixture over a heated copper gauze. The mixture of gases so produced is collected over an aqueous solution of potassium hydroxide which absorbs carbon dioxide. Nitrogen is collected in the upper part of the graduated tube. Let the mass of organic compound mg, volume of nitrogen collected V1 ml, room temperature T1 Kelvin, volume of nitrogen at STP is equals to P1V1 into 273 upon 760 into T1. Let it be V ml. It means V is in ml, where P1 and V1 are the pressure and volume of nitrogen. P1 is different from the atmospheric pressure at which nitrogen gas is collected. The value of P1 is obtained by the reaction. So P1 is equals to atmospheric pressure minus aqueous tension. So that is 22400 ml N2 at STP weighs 28 gram. 12.15 Dumas method diagram you can see here. V ml N2 at STP weighs is equals to 28 into V upon 22400 gram. Percentage of nitrogen you can see here. Second one is the Jaldal methods. The compound containing nitrogen is heated with concentrated sulfuric acid. Nitrogen in the compounds gets converted to ammonium sulfate. The resulting acid mixture is then heated with excess of sodium hydroxide. The liberated ammonia gas is absorbed in an excess of standard solution of sulfuric acid. The amount of ammonia produced is determined by estimating the amount of sulfuric acid consumed in the reaction. It is done by estimating unreacted sulfuric acid left after the absorption of ammonia by titrating it with standard alkali solution. The difference between the initial amount of acid taken and that left after the reaction gives the amount of acid reacted with ammonia. Organic compound plus H2SO4 gives out NH4 whole twice SO4 gives out 2NaOH, Na2SO4 plus 2NH3 plus 2H2O. 2NH3 plus H2SO4 gives out NH4 whole twice SO4. Let the mass of organic compound taken Mg and volume of H2SO4 of molarity M taken is equals to V upon Vml. You can see the remaining calculation here. So finally we are getting the percentage of nitrogen is 14 into M into 2 in bracket V minus V1 upon 2 bracket close upon 1000 multiplied by 100 upon M. The final value we are having 1.4 into M into 2 V minus V1 upon 2 whole upon M. Jaldal method is not applicable to compounds containing nitrogen in nitro-azo group and nitrogen present in the ring, example pyridine, as nitrogen of these compound does not change to ammonium sulfate under these conditions. 12.10.3 Halogens. Carius method. A known mass of an organic compound is heated with fuming nitric acid in the presence of silver nitrate contained in a hard glass tube known as Carius tube. Figure 12.17 you can see here, Carius method. Halogen containing organic compound is heated with fuming nitric acid in the presence of silver nitrate. In a furnace, carbon and hydrogen present in the compound are oxidized to carbon dioxide and water. The halogen present forms the corresponding silver halide AgX. It is filtered, washed, dried and weighed. Let the mass of organic compound taken mg. Mass of AgX formed m1g. 1 mole of AgX contain 1 mole of X. So mass of halogen in m1g of AgX is equals to atomic mass of X into m1g and molecular mass of AgX. 12 point percentage of halogen is here atomic mass of X into m1 into 100 upon molecular mass of AgX into m. 12.10.4 sulfur. A known mass of an organic compound is heated in a carrier tube with sodium peroxide or fuming nitric acid. Sulfur present in the compound is oxidized to sulfuric acid. It is precipitated as barium sulfate by adding excess of barium chloride solution in water. The precipitate is filtered, washed, dried and weighed. The percentage of sulfur can be calculated from the mass of barium sulfate. Let the mass of organic compound taken mg, and here you can see the complete calculation, and the percentage of sulfur we are finally getting 32 into m1 into 100 upon 233 into m. 12.10.5 phosphorus. A known mass of an organic compound is heated with fuming nitric acid, whereupon phosphorus present in the compound is oxidized to phosphoric acid. It is precipitated as ammonium phosphomolybdate by adding ammonia and ammonium molybdate. Alternatively, phosphoric acid may be precipitated as MgNH4PO4 by adding magnesium mixture which on ignition yields Mg2P2O7. So here you can see its calculation. The final percentage of phosphorus we are getting here 62 into m1 into 100 upon 222 into m%, where 222U is the molar mass of Mg2P2O7 m, the mass of organic compound taken m1, the mass of Mg2P2O7 formed, and 62, the mass of 2 phosphorus atoms present in the compound Mg2P2O7. 12.10.6 Oxygen. The percentage of oxygen in organic compound is usually found by difference between the total percentage composition and the sum of the percentage of all the other elements. However, oxygen can also be estimated directly as follows. A definite mass of an organic compound is decomposed by heating in a stream of nitrogen gas. The mixture of gaseous products containing oxygen is passed over red hot coke when all the oxygen is converted to carbon monoxide. This mixture is passed through warm iodine pentoxide when carbon monoxide oxidized to carbon dioxide producing iodine compound. On heating, it is giving O2 plus other gaseous product. You can see here the two reactions. On making the amount of CO produced in equation A equal to the amount of CO used in equation B by multiplying the equation A and B by 5 and 2 respectively, we find that each mole of oxygen liberated from the compound will produce 2 moles of carbon dioxide. Thus 88 gram carbon dioxide is obtained if 32 gram oxygen is liberated. So here you can see the calculation, and the final percentage of oxygen we are getting here 32 into m1 into 100 upon 88 into m%. The percentage of oxygen can be derived from the amount of iodine produced. Presently, the estimation of elements in an organic compound is carried out by using micro quantities of substances and automatic experimental techniques. The elements carbon, hydrogen and nitrogen present in a compound are determined by an apparatus known as CHN elemental analyzer. The analyzer requires only a very small amount of the substance 1 to 3 mg and displays the value on a screen within a short time. A detailed discussion of such methods is beyond the scope of this book. Summary. In this unit, we have learned some basic concepts in structure and reactivity of organic compounds which are formed due to covalent bonding. The nature of the covalent bonding in organic compounds can be described in terms of orbital hybridization concept, according to which carbon can have sp3, sp2 and sp hybridized orbital. The sp3, sp2 and sp hybridized carbons are found in compounds like methane, ethene and ethine respectively. The tetrahedral shape of methane, planar shape of ethene and linear shape of ethine can be understood on the basis of this concept. A sp3 hybrid orbital can overlap with one s orbital of hydrogen to give a carbon-hydrogen single bond, that is sigma bond. Overlap of a sp2 orbital of one carbon with sp2 orbital of another results in the formation of a carbon-carbon sigma bond. The unhybridized p orbitals on two adjacent carbons can undergo lateral overlap to give a pi bond. Organic compounds can be represented by various structural formulas. The three-dimensional representation of organic compounds on paper can be drawn by wedge and dash formula. Organic compounds can be classified on the basis of their structure or the functional groups they contain. A functional group is an atom or group of atoms bonded together in a unique fashion and which determines the physical and chemical properties of the compounds. The naming of the organic compound is carried out by following a set of rules laid down by the International Union of Pure and Applied Chemistry (IUPAC). In IUPAC nomenclature, the names are correlated with the structure in such a way that the reader can deduce the structure from the name. Organic reaction mechanism concepts are based on the structure of the substrate molecule, fission of a covalent bond, the attacking reagents, the electron displacement effects, and the conditions of the reaction. These organic reactions involve breaking and making a covalent bonds. A covalent bond may be cleaved in heterolytic or homolytic fashion. A heterolytic cleavage yields carbocations or carbanions, while a homolytic cleavage gives free radicals as reactive intermediate. Reactions proceeding through heterolytic cleavage involve the complementary pairs of reactive species. These are electron pair donor known as nucleophile and an electron pair acceptor known as electrophile. The inductive resonance, electromeric, and hyperconjugation effects may help in the polarization of a bond, making certain carbon atom or other atom positions as places of low or high electron densities. Organic reactions can be broadly classified into following types: substitution, addition, elimination, and rearrangement reactions. Purification, qualitative and quantitatively analysis of organic compounds are carried out for determining their structures. The methods for purification, namely sublimation, distillation, and differential extraction, are based on the difference in one or more physical properties. Chromatography is a useful technique of separation, identification, and purification of compounds. It is classified into two categories: adsorption and partition chromatography. Adsorption chromatography is based on differential adsorption of various components of a mixture on an adsorbent. Partition chromatography involves continuous partitioning of the components of a mixture between stationary and mobile phases. After getting the compound in a pure form, its qualitative analysis is carried out for detection of elements present in it. Nitrogen, sulfur, halogen, and phosphorus are detected by Lasignase test. Carbon and hydrogens are estimated by determining the amounts of carbon dioxide and water produced. Nitrogen is estimated by Dumas or Gildan methods, and halogens are by Carius method. Sulfur and phosphorus are estimated by oxidizing them to sulfuric and phosphoric acids respectively. The percentage of oxygen is usually determined by difference between the total percentage 100 and the sum of percentages of all the elements present. चैप्टर डन. थैंक यू सो मच एवरीवन फॉर लिसनिंग दीज ऑडियो बुक्स. आज थोड़ा कोल्ड होने की वजह से हो सकता हो आप लोगों को मेरी वॉइस थोड़ा डिफरेंट लग रही हो और इसी की वजह से थोड़ा सा आपकी ऑडियो बुक ये डिले हो रही है, बट मेरी कोशिश है कि मैं जल्द से जल्द आपकी बाकी भी 12th क्लास की जो बच रही है उनको पूरा कर दूँ. सो आपकी जो भी रिक्वायरमेंट है यू कैन टेल मी इन द कॉमेंट सेक्शन. So I hope that you enjoyed, and don't forget to press the like button and share with your friend also. Bye bye everyone. Take care. If you are new on my channel, then please subscribe. Bye bye. Just stay tuned with me. Take care.